Welcome back, Geos406 students. In this module, you're going to calculate flow conditions in a volcanic conduit during an eruption. I love this module. This is one of the ones developed by Chuck Connor at the University of South Florida. I made some few modifications to it, but this is really all of his work. And this is a really nice, neat, simple way of connecting volatile solubility with equilibrium, degassing, or exsolution, and magma ascent velocities, and then exit velocities and fragmentation conditions in the conduit. So you're going to use some simplified equations of state to model a steady state Plinian eruption. So you're actually going to be doing a one-dimensional magma ascent and degassing and velocity model. And it's a really nice, neat module, I think, that helps you gain a hands-on appreciation for how to create a conduit flow model. So this is focused on Plinian-style eruptions where we have steady state conditions. That just means that you have magma rising up in the conduit of the volcano, erupting from the vent, and this eruption is going to last for hours to days. And during that time, you have set up some steady state conditions in the conduit. So you're not shutting the magma supply off, you're not creating fluctuations or episodic explosions. This is just a continuous outpouring of magma from the vent of the volcano. So these Plinian-style eruptions are intense and energetic. They last for a long time. They're very hazardous because they can eject ash and gas into the atmosphere, and this process can last hours to days. They often result in potentially deadly pyroclastic density currents and lots of ash fall downwind. Ash clouds from Plinian eruptions can go thousands of miles or kilometers downwind and interrupt international air traffic. So these eruptions typically produce large volumes of pyroclasts, so greater than 10 to the 10th kilograms, and they produce high altitude ash clouds, greater than 20 kilometers. So there's a couple of pictures from the USGS. The top is the classic May 18th, 1980 eruption of Mount St. Helens. The bottom photo is Pinatubo in 1991, both Plinian-style eruptions. So Plinian eruptions appear to happen when you have large volumes of magma that flow up the conduit to the surface very quickly. So magma ascent rate is really fast. The magmas are typically higher in SiO2 content. They're more viscous. They contain significant gas and volatile contents. The flow conditions in the conduit are often steady or nearly steady state, and this produces a fire hose-like geysering of ash, fragmented magma rushing out of the volcano. And this is caused by pressure in the magma reservoir. And only when the magma reservoir starts to empty appreciably or the pressure in the reservoir starts dropping, that's the point at which you actually can have this eruption style tail off and then stop. But this only usually happens when the volcano's erupted a lot of magma. So here's a cartoon cutaway of a volcanic conduit by Gonnerman and Manga, and it shows some of the different parameters we talked about in one of the prior lectures. So a volcanic conduit can have several different flow regimes, so this is review material at this point. The reservoir starts in an overpressured state, and that magma reservoir starts to drive magma flow up the conduit because it's got higher pressure down here in the reservoir than up at the top. As the magma ascends, the bubbles nucleate and then grow and expand and coalesce. Bubble expansion can help accelerate flow because you're in a confined space, so the volume expansion is hindered, and that results in an increase in bubble overpressure. Bubble coalescence can lead to fragmentation then, once the magma reaches a critical bubble volume fraction or strain rate, and we talked about this with your Module 3. Okay, so your problem. Given pressure conditions in a volcano conduit as a function of depth, what is the ascent velocity of that magma? You're going to calculate that as well as answer some questions related to exit velocity and fragmentation depth. So first you're going to use Henry's law and conservation of mass to estimate ascent velocity. So you learned about Henry's law during the solubility module 2, and we're going to use it here again to do something really interesting. We're going to use it to calculate how fast that magma is flowing up the conduit. So first we're going to have some assumptions here that are pretty simplistic, so keep that in mind. We're going to assume a one-dimensional steady state magma flow. That means you have magma that's just flowing up and there's nothing happening to the sides. The pressure profile in your conduit is known. So we know what the pressure is at the bottom, and we know what it is at the top, and we know what it is all throughout the ascent pathway in between. We're going to solve for velocity from pressure using Henry's law. And you're going to assume that Henry's law applies, and you're going to ignore any funny things like supersaturation for the time being. If you don't know what that means, just disregard. You're going to assume that Henry's law is the gold standard for what's happening in this conduit during your model eruption. You can also assume that no gas is lost from the magma. So all of the exsolved gas is retained in the bubbles, and then it comes out the top after fragmentation. This is an important assumption. Think about it. Some gas could be lost through the walls of the conduit. Maybe there are other ways gas could leave the system rather than just going into bubbles and then erupting after fragmentation. Okay, so you're going to use a different formula for Henry's law than you used in the Module 2, and this is going to be retooled so that you can estimate the amount of exsolved gas from an initial dissolved concentration of gas in the melt. So I have a cartoon here that shows red magma with white bubbles. So you have mass fraction of volatiles. We're going to assume that everything is conserved here. That means that the mass fraction of volatiles dissolved in the melt is going to be estimated using Henry's law. And then you have a mass fraction of exsolved volatiles that have already entered the bubbles. And you're going to do a mass balance to try to figure out what that is. So the initial volatile fraction is equal to the mass fraction dissolved in the melt, which you're going to determine using Henry's law, plus the mass fraction that is exsolved into the bubbles. So the mass fraction of exsolved volatiles in the magma at any given pressure is given by this formula of Henry's law, which is NEx, that's the exsolved mass of the volatiles in the bubbles, is equal to N sub 0, that's the initial mass fraction of volatiles dissolved in the melt before any bubble formation takes place, minus S, which is a constant, times P to the beta, which is going to be your exponent here for Henry's law. So you're going to use this formula for Henry's law to estimate the solubility of water in the magma and the mass fraction of water exsolved from the magma. So Henry's law, again, gives the solubility as a function of pressure, assuming that the magma is in equilibrium. So that means that there's no funny business going on. All of the water that's in there is going to perfectly go into the bubbles along the pressure curve as determined by Henry's law. So the mass fraction of exsolved volatiles can be calculated if you know the initial volatile content in the magma. So in this case, we have N sub S, which is the solubility of water in a rhyolite magma, and it's going to be times 4.1 times 10 to the minus 6, which is your K constant, times the square root of pressure. So we're going to do a little mass balance equation here next, which N sub EX is equal to N sub 0, which is the initial volume, or the initial mass of volatiles in the system, minus N sub S, which is the amount of volatiles that remain dissolved in the melt, divided by 1 minus N sub S. So these are the equations you're going to use to estimate volatile solubility and then the amount of exsolved volatiles in the bubbles. So now you want to calculate the density of the ascending magma, and this is where you're going to estimate ascent velocity. So this is the next step in that process. The density of the magma, in this case, the mixture of melt and bubbles, can also be estimated using the ideal gas law. So in this case, the density of a mixture under specific pressure conditions, assuming Henry's law applies, is given by this equation here, where 1 divided by the bulk density of the magma is equal to the mass of exsolved volatiles times R times temperature divided by pressure, this is the ideal gas law, plus 1 minus the fraction of exsolved volatiles divided by the density of the magma. So this is just taking ideal gas law and putting it into a mass balance equation form by substituting volume with density. So bulk density is the density of the magma mixture, so that's magma plus gas bubbles in total. Density of the magma is density of just the magma part, and that's just the melt part. N sub EX is the mass fraction of exsolved volatiles that you calculated from the prior slide. R is the ideal gas constant expressed in terms of mass, and it's given here, 462 joules per kilogram per Kelvin for water vapor. T is temperature in degrees Kelvin, and P is pressure in pascals. So you're going to need to check the units of your equation. Note that the gas constant for water vapor is expressed in terms of joules per kilogram per degree Kelvin. So what are normal units of the gas constant, and what assumption is being made in expressing the units about the volatiles in the magma? So this is just a side question you can ponder. Okay, last step, you're going to take the bulk density of the magma. It's going to be changing as you exsolve more and more volatiles as pressure drops, and you're going to calculate flow velocity from this. So once the density of magma as a function of depth is estimated, it's possible to estimate the velocity of flow along the conduit for a given mass. In this case, a one-dimensional velocity is calculated. So that is, the velocity is assumed not to vary from the center to the edges of the conduit. So this isn't simple pipe flow. This is just magma moving up in one direction. The actual velocity is going to be different. It's going to be higher in the center and lower at the edge of the conduit, but we're going to ignore that for this simple model. So we're going to use a rearranged form of mass flow from last time, where Q is mass discharge rate or mass eruption rate in kilograms per second. U is average velocity. Pi r squared, that's an area term. R is the radius of the cylindrical conduit. And then rho bulk is the bulk density of the magma, which varies as a function of depth. And that's what you calculated in the prior slides. So this rearranged form of the mass discharge rate equation that you learned about in the prior lecture can give you ascent velocity of the magma as a function of the bulk density of the magma as it changes as magma rises up to the surface. So you're going to make a spreadsheet to calculate ascent velocity from the prior equations, and you're going to be given a bunch of different constants. So I want you to take careful note of this slide, because all of the constants given up here for initial volatile content, the Henry's law S, the Henry's law beta exponent, magma temperature, magma density, gas constant R, mass eruption rate, and conduit radius are given in these cells right here. So these are the constants you're going to want to use for your homework problem set. And the units are given in the adjoining column. So you're going to calculate ascent velocity over a depth range in meters that's given to you in this column here, and pressure in megapascals here. You're going to calculate solubility, the mass fraction dissolved in the melt. You're going to calculate the mass fraction of volatiles exsolved in the bubbles. You're going to calculate bulk density, and then from that you're going to calculate exit velocity and porosity of your magma in percent volume percent vesicles. So I'm not going to make you type all of these things in here. So your pressure and depth profile is given to you in a worksheet that you can download from Blackboard. It's also linked into this PowerPoint, so you can just open it up from PowerPoint if you want as well. To do that, all you need to do is exit slideshow view and double click on this red square, and it'll bring up the embedded Excel spreadsheet. In that Excel sheet, you have depth and pressure, so that gives you the depth and pressure profile you'll need to calculate all of the other parameters for your model. Okay, I know that seems like a bunch, but you're going to go through this step by step, and you can always ask me if you have questions or you get stuck. So first, read through this PowerPoint file completely before getting started. Then read through the Word document homework assignment, because that'll lead you through this homework assignment step by step. Write down all of the slide numbers and equations you need to solve the problem so you have them handy for when you set up your spreadsheet. And download the pressure depth profile Excel sheet from Blackboard to give you your starting point so you don't have to type all of those numbers in yourself. You can make this model in Excel, or you can use another spreadsheet program like Google Sheets. There are no embedded macros in here, and you'll be coding in the calculations you need to perform in your spreadsheet yourself. And then, as always, let me know if you have questions or get stuck. Good luck, and I hope you have fun calculating your one-dimensional conduit flow velocity model.